Hi, it's Mr. Mac, and we're going to be doing 4 calculation questions, one from advanced mechanics, one from electromagnetism, one from the nature of light, and one from the module from the universe to the atom. And then we will look at a written response question.
Welcome to Mr. Mac's Physics channel. He can explain things really well and is a lot of fun to watch.
Here's the question we've got. Now, in the short time we have, I can go through as many of those questions as possible. Question 1 comes from a physics Olympiad in 2008. A bird flying in a straight line, initially at 10 meters per second, uniformly increases its speed to 18 meters per second while covering a distance of 40 meters. Okay, what is the magnitude and acceleration of the bird? So this question obviously is a calculation question. So the data, so get to there. This is question 1, and U is 10 meters per second. So B equals 18 meters per second. And we know that the displacement is 40 meters. So S equals 40 meters. Now, even though it's there in the question, it's really important to write those things down and work out what we're trying to find. And of course, it's acceleration. So you want to choose a formula that has those given ones, U, V, S, and A. But of course, it's the A that we want to find. Now, what formula do we have for that? It's the V squared equals U squared plus 2AS. 10 squared plus 2 times A times 40. So now we can see the A is the only polynomial, so we get that to the left and all the numbers to the right. That's making A the subject. A equals 18 squared minus 10 squared all over 2 times 40. And that we can go straight into the calculator and we should end up with 2.8 meters per second squared. At this point, we need to just check that everything's okay. Does that make sense? 2.8 meters per second squared, yes, accelerating from 10 to 18 over a distance of 40 meters, that's sensible. And of course, check MUDs, magnitude, check the units, meters per second squared, and then check also for direction. If it's an acceleration, you can put the direction as being the direction the bird's flying, and significant figures, we can say 2 significant figures. And just to state that to the marker says that you know what you're doing. Okay, that's question 1. Question 2, we have 2 electrons placed 1.5 nanometers apart. Calculate the electrostatic force acting on each electron. It's actually on the data sheet. So we'll put that down just so that we know where it is. Minus 1.602 times 10 to the negative 19 coulombs. And now the distance they are apart is, we're going to call it R, and it's 15 nanometers. So if R is 15 nanometers, what's that in SI units? So we have to then say, well, what does nano mean? Nano, negative 9. And so it's 15 times 10 to the negative 9, or 1.5 times 10 to the negative 8 meters, changing it to meters and scientific notation. And we put it in scientific notation because it's easy to put on the calculator. And then the next thing is we've got this constant, epsilon 0, again from the data sheet. Epsilon 0 is 8.854 times 10 to the negative 12. We want to find the force. So F equals something. And in this case, we're going to use the formula for the force between 2 electric charges. We have the constant at the beginning, 1 over 4 pi epsilon 0 times Q1, Q2 all over R squared. So when we substitute, we should have, on the top line, we've got two charges that are equal. So I'm just going to substitute in QE, which is 1.602 times 10 to the negative 19, and I'm going to square that on the calculator. That'll save a step. On the bottom is 4 pi times epsilon 0 is 8.854 times 10 to the negative 12. And we want to multiply that by r squared. Remember, r is 1.5 times 10 to the negative 10 to the negative 8. 1.5 times 10 to the negative 8, and it's squared. Okay, so that means it's a nice simple calculation. We only have 1, 2, 3, 4, 5 numbers to substitute into, put into your calculator. Remembering to use some scientific notation, the nice, quick and easy way. And that should give you the force as 1.025 times 10 to the negative 12 newtons. Now, significant figures are interesting because we've been given only 15 in the question, which is 2 significant figures. So really, we can wipe out these and tell the examiner we do know what we're doing, and just say 2 sig fig. So we need to check that it's reasonable. 10 to the negative 12 is quite a small force. That makes sense. We're dealing with electrons that are very close together. So check MUDs, magnitude, units, direction, significant figures. So magnitude is fine. Units, newtons, because it's force. Direction. So we actually need to state this. Is the direction up, down, left, right, north, south, east, west, repelling, attracting? What's it doing? It's repelling. So we need to state that. It's a force of repulsion, but I'll just put the word repelling there. So question 3 is a star X has a surface temperature of 30,000 Kelvin. Determine the wavelength at which star X would emit the most intense electromagnetic radiation. Calculation question. So what's the first step? Is 30,000 Kelvin. That's nice. It's in Kelvin. We can deal with Kelvin. We've got on our formula sheet the constant. It says it's little b. Little b is 2.898. And you can see I can't remember it. Times 10 to the negative 3. So check that it's SI, and then it's a nice simple substitution into this formula. Lambda, now remember this is lambda max, is B over T, that's Wien's law, and that's a very useful one to find the surface temperature of the sun or of any star, or in fact anything that's a black body radiation and glows. It tells us the surface temperature, which is very useful. So we just substitute. So 2.898 times 10 to the negative 3 over 30,000. Put that in the calculator. And you should get something like 9.66 times 10 to the negative 8. And it's in meters. And let's just check that it's reasonable. To check that it's reasonable, it's 10 to the negative 8 meters. Now that's close to nanometers. Remember, nana, negative 9. So that's actually useful because we know our electromagnetic spectrum in the wavelength in nanometers. And that's a very useful thing to remember, just to make sure that we can check. Remember, we're checking MUDs, magnitude, units, direction, if it's a vector, and significant figures. Now, this is not a vector, but we certainly want to check that this is a reasonable answer. So that's the magnitude. And it is, because it turns out to be 96.6 nanometers to 3 significant figures. And again, just tell the person marking that you know what you're doing. It's very ambiguous in the question. Is that 1 significant figure, 2, 3, 4, or 5? You could say 5 if you wanted to, you could say 3. So unless you're told to round it, get in the habit though of making sure you include that in your answer. So we're up to question 4. How is Rydberg's constant R related to the longest wavelength, lambda alpha, emitted from the Balmer series of the hydrogen atom? So it's modulate, and we're looking at the Balmer series is when we're looking at the hydrogen atom in particular, and looking at the energy levels and being able to calculate changes in those energy levels. So this is quite a complex one. Remember that Bohr said, that's Niels Bohr, that the longest wavelength of the Balmer series would be produced when an electron moved from n equals 3 to n equals 2. That's going to be the longest wavelength produced. And so we're going to use those as additional information that's implied in the question. Okay, so it's a direct implication of the word longest, okay, that term longest wavelength. So that means we've got n final is 2 and n initial is 3. And we know the Rydberg constant is what we want to find, and we want to then relate that to lambda. So in fact, that's the only data we have. But we have a very complicated looking formula that's very, very useful. And the reason I've thrown this in to do today is because it's important that we see that sometimes we don't get a number for an answer, but we get a relationship. And that's what this question is about. So what is the formula that we need? It's this one, 1 over lambda equals big R brackets. And then we've got a complicated looking expression. It's important that we get this right, not only when we're writing it, but how we do it on the calculator. You'll see what I mean in a minute. So it's 1 over nf squared minus 1 over ni squared. So that's the final energy level. That's the initial energy level. Remember that we need to square them, take their reciprocals, and subtract them in that order. If we subtract them in the opposite order, we might get a negative number. And then we go back to the question and say, well, what are we doing? Are we putting energy in which case the electron will jump up a level, or is it relaxing back to its ordinary state, in which case it gives out a photon? Well, in this case, we've got it the right way around. We've substituted correctly, and so this is lambda alpha. 1 over lambda alpha is R. We're going to leave that for the time being and do the calculation in here when we're substituting is 1 over 2 squared minus 1 over 3 squared. You get a mark for this line here. So this might be a 2-mark question, or it might be a really nasty multiple choice question. And I say really nasty because it might give you 4 alternatives and you have to check. You work it through from scratch and you eliminate the ridiculous one, and then you work out you've got 2 possibilities. You've got to calculate both of them and see if they're right. But if this was a calculation question in the second section, that's where you get your first mark. Substitute correctly into the correct formula. And then do the calculation. Now we want a relationship between these two, so we're just going to look at the brackets. So 1 over 2 squared, that's a quarter. 1 over 3 squared, that's a ninth. A quarter minus a ninth, get a common denominator and so on, you end up with 5 on 36. And I would suggest, so we don't get confused or upside down or anything like that, that you write it as 5 over 36 as a separate line. So we've got lambda alpha equals 36 over 5, and that looks a lot better. That's the answer to the question. So we're up to question 5. And question 5 is simply outline de Broglie's hypothesis and explain how it was experimentally verified. It's a 5-mark question. So this is one of these longer written response questions. We need to sort out a plan of how we're going to answer this. In an exam, spend half a minute or so actually working out how you're going to attack this particular question. Now, it does say that we've got to outline de Broglie's hypothesis, so part one, and the second part is to explain how it was experimentally verified. So these are two parts. So one is de Broglie's wave-particle nature of matter hypothesis. And that makes sense, okay? We're wanting to see how de Broglie has a wave-particle nature of matter. That was his hypothesis. And I'll break that up in a minute, but let's look at part two, which is the experimental evidence. And I'm just going to see if I can change colours so you can see it a bit better. In part one, we want to have reference to the wave-particle nature of light. So this is built up from what we already know in the nature of light. So that's going to be our first point, the wave-particle nature of light. Because that's the basis of de Broglie's hypothesis about matter. And the second thing that we want to say is actually put in an equation. And we want to put in the wavelength equation where we put together Planck's constant, that's energy equals h times f, and Einstein's matter-energy equivalence equation, which is E equals mc squared. And they put them together and you get the wavelength equation. Wavelength equation starts with lambda as the wavelength, and it's h over mv. This is our outline of where we're going, and I'll go through a sample response in a minute. For the experimental evidence, we're going to have some dot points here as well. Firstly, we're going to start with the experiment that Davison and Germer did. If you're not familiar with those names, you need to go and have a look at your text and find out a little bit about the experiments. But what they did is they fired electrons at some nickel that they'd heated up. So we need to outline that. That's pretty important as part of the question here. Secondly, we need to do the observations from that. And what did they observe? They observed interference patterns. And thirdly, we then want to say, this is an explain question, so very key in our mind is therefore or hence, or this causes that. So hence, they are matter waves. There's interference, hence they are matter waves. And the fourth point that we want to say is the wavelength of electron waves agrees with de Broglie's hypothesis. So we're going to bring it all together. So the wavelength of an electron agrees with de Broglie's hypothesis. Now that's really important. And look, what did that take? About a minute? Perhaps a bit longer. If you jot that down, I've actually got a quote here that I want to put into the sample response, or in your exam, your answer. You can say, hence they are matter waves, and just quote it straight away. Okay, that outline is going to be key, and each one of these dot points will be a separate paragraph. I've got 6 paragraphs to write. Well, with those 5 questions answered, I hope you do really well in your exams in physics. I'm Mr. Mack. Thanks for watching.